Okay, so do you remember the difference? Okay, right. So we will move to the next part then. Okay, now we will discuss about the equation. Okay, samarium neodymium system equation. So I think you can remember the derivation of the equation. Whatever the system, the same procedure is there. So what you have to consider is initial isotopic composition. You need to know. Oh, sorry. Initial isotopic ratio you need, right? Initial number of isotopic atoms of daughter and ratio, and then the radiogenic product, right? So this star indicates the radiogenic product. Okay, so this one, radiogenic product, right? So this radiogenic product is equivalent to this term, because this is the parent samarium, right? This decays into neodymium. So that's why we take this with the decay constant, right? Decay constant we have here, lambda, and with the time frame of t, you have it here. So initial amount of daughter isotope is here, that plus the radiogenic product, right? Initial amount plus the radiogenic product over t time interval will give you present day entire amount of dot isotopic amounts, right? So since we use this as a ratio, like in the rubidium strontium system, we take neodymium 144 as the stable isotope, which does not change, uh, change with time. I mean, it is not radiogenic. Okay, it's stable. So no harm to use that amount to divide or to normalize. So that's why we divide that and we represent it as a ratio. And initial ratio is here, initial neodymium ratio is given here, and this is the parent daughter ratio, and the decay term is giving, ultimately providing us the final equation. Okay, so radiogenic product of neodymium isotope measured today equals, this is today, t equals 0, right? Present day isotopic measurement, right? And this is present day uh, isotopic ratio, samarium neodymium isotopic ratio. This is present day. So this ratio we use to find out how much the radiogenic component. So this is the radiogenic component over time t period. So we have the time t period, the term here and lambda here. So all this term will give you the radiogenic product, radiogenic amount. So that is added by the initial amount that's given by this value. Okay, so this one we can measure, and this one we can measure, but time we don't know. Okay, time we don't know, that's what our concern, and initial amount also we don't know, right? So we put this in y equals mx plus c type of a diagram, and with the uh, gradient we can calculate the t, and with the intercept we can calculate the initial ratio, the same as the rubidium strontium isotopic system. So this is the radiogenic decay equation. So you have to remember this radiogenic decay equation, okay, in the rubidium strontium system as well as samarium neodymium system. You have to remember. Okay. So we'll see this equation, and these measurements, normally we consider these measurements using a mass spectrometry as I mentioned before, but we use a special technique called isotope dilution method. Okay, we use something called isotope dilution method, which I'm not going to introduce. It's a different technique. Okay, some analytical protocol which you don't need at this level. Uh, but just to mention you, we add another isotope to the sample. I mean, it's in a liquid form, right? It's a concentrated isotope in a liquid form. We have some solutions for that. For the mass spectrometry, we have some standard solutions, right? So one of those solutions we have for these isotopic systems, and we add that drop into our sample, because we have to measure very tiny amount of sample, the powder, right? We have to crush the sample and make a powder, tiny powder, less than 200 micrometer size, grain size, uh, very fine grain. And out of that powder, we weigh about 50 milligrams of sample powder, right? And that is put into a Teflon beaker. Teflon beakers, right? It can resist high temperatures and digest with acid. What are the acids used for rock digestion? Did you learn under analytical techniques in geology in your third years? For rock digestion, what are you going to use? The acids: hydrofluoric, perchloric, nitric, sometimes HCl, concentrated HCl. Okay, some mixture of these acids will be used to digest the rock sample. So it will digest all the minerals there. Sometimes you can't digest zircon like minerals, but still there is possibility to digest zircon if you use high temperature furnace. Okay, high temperature furnace, kind of an fusion, kind of a fusion technique, right? uh, but zircon does not matter much in these isotopic systems, because zircon does not contain a lot of samarium, neodymium, or rubidium, strontium. But for uranium lead, if you do, it matters. Okay, so therefore, even zircon is remaining there without digestion, no problem, right? You can take the solution, and you have to do some stepwise drying process. Okay, at different degrees, because now your sample is dissolved or digested in acid now, right? You have to evaporate the acid. You can't evaporate all the acid together, because their evaporation temperatures are different. Perchloric is different, HF is different. So you need different evaporation methods. So we do this in a stepwise manner, uh, gradually, maybe starting from like 80 degrees Celsius on a hot plate in a closed cupboard, like a fume hood. You can use a fume hood, but it should be closed. Uh, and then from 80 degree, you will evaporate all the water there, because diluted acid contains some distilled water, right? Diluted water. And then use gradually increase the temperature to 100, 105, and then 115, 120, like that. So when it reaches 120, finally the perchloric acid will be evaporated, right? By that time, HF has already gone, right? By when you reach 120 degrees. So this should be very slow process, right? Otherwise, your sample will you will lose all some of these elements as well. Okay, and then this dried sample, actually you can't see anything on the bottom of the beaker now, because acid has evaporated, but there should be some elements remaining on the bottom of your uh, beaker, right? Teflon beaker, very small Teflon beaker, like 2 centimeter high, 1.5 centimeter like diameter. You have to handle it very carefully, because you are dealing with isotopes now, not just the elements. You are going to deal with isotopes, right? Now you have elements after evaporation, but now you have various types of elements, because this is your rock, your digested rock. It contained a lot of minerals, say garnet, quartz, feldspar, amphibole, mica, everything was there. So all the elements that constituted these minerals are now lying on your bottom of the beaker, right? So you have to separate samarium, neodymium to measure, right? If you are measuring rubidium, strontium, then you have to separate rubidium, strontium from that dried sample. How can you do that, right? You can't see anything, right? Nothing you can see. I mean, you can't see even a like a film, like I mean, a tiny film of sample. No, you can't see, right? Nothing. So uh, yeah, maybe by an SCM you can see, but for your naked eye you can see nothing. Then you need to use a special kind of a resin, and you have to put it into a what do you call a column, right? We use column chemistry, a procedure called column chemistry. Maybe in chemistry, I don't know whether anybody has that experience using columns, ion exchange columns, right? So we have to put our sample into a column which contains a resin. So this resin can absorb some elements. So and some other elements can be passed through the resin. So what we do is we pass our sample through this column, this resin. Okay. Uh, uh, to do that, you have to redissolve the sample, because this is now dried. You can't, how can you pass it to the column? So you have to dissolve it anyway. So what you do is you have to take a very, very pure acid, not the acid that you use for digestion. It is less pure. It's not industrial actually, but it's analytical grade. But more pure distillated acid has to be used at the second step of dissolution. So once you use like nitric acid, distillated nitric acid, and dissolve your sample with a few milliliters, and then you pass it through the column, right? When the sample solution goes to the column, some of the elements like magnesium, potassium, iron, like heavy elements, will be easily absorbed to the column, and the remaining elements will be passing through, especially the rare earth elements and other trace elements will be passing through the column without problem. And you have to collect the new solution uh, into a new beaker. Okay, right. Then this new beaker again has to be dried, like in the previous case, stepwise drying. And then you have to dissolve it again with distillated nitrate. And then you have to do a second step of column chemistry, right? For that, you have to use another type of resin, which can attract some trace elements, right? So likewise, this process goes in like 3 steps method. And finally, the samarium neodymium will be collected. I mean, all the other trace elements will be absorbed in the resin, but experimentally, it has been determined the best yield by repeating experiments like this, right? So likewise, people know how much acid has to be passed through this column for how many minutes, or how many hours, like, right? So optimized condition has been determined by experimental methods. So accordingly, we have to do this process, and finally, you collect this samarium and neodymium into a beaker. These elements then will be again in a solution. I mean, first you have to dry again at last step also. Finally, you have to dissolve it with the very tiny drops of nitric acid again, and use it for the mass spectrometry. That tiny drops of your sample solution has to be used for the mass spectrometry. So you started with the 50 micrograms, 50 milligrams of sample, but you end up with some nanograms of samarium and neodymium at the end, right? So that tiny amount is injected in a solution to the mass spectrometer to find out these isotopic ratios. So this is how you have to do this isotopic analysis. It is a very tedious task. Okay, it's a very difficult task, but you have to. I mean, once you get used to it, you can do it very efficiently, right? So this is how we do this isotopic analysis. Anyway, it is at the beginning it's very tedious and very boring and very I mean frustrating, because sometimes you end up with nothing after maybe 2 weeks, or yeah, at least 10 days you have to follow this procedure of work, then you have to repeat. That's very disappointing, but when you get the experience, you will do it very frequently, very efficiently also, right? So anyway, so this is how we determine the isotopic ratio. So such determinations will give you this number and also this number. Okay, so these numbers, once known, we can plot in a diagram. Here you can see that diagram. For the samaritan neodymium system, what we use is this ratio, right? That is this one and this ratio, right? Like the rubidium strontium, the similar way. You remember y equals ms plus c. So here you see y and x, and intercept, you get the initial ratio, and from the gradient you get the date or the time t, age of the rock. So this is an example showing mineral, two minerals, pyroxene and plagioclase, and whole rock. Actually, this is the best way to do. You have to do, you can do multiple whole rock samples, right? You can take several whole rock samples from the same rock and do an isochrone, right? That is okay. But if you take some mineral, you have to, I mean, after separation of some minerals from the same rock, you dissolve those minerals with the and whole rocks separately, and you measure uh, to plot in a isotopic diagram. So then you will get more accurate isochrone, because it will show you, if they lie on a single line, it will indicate all the minerals plus whole rock has remained in a closed system. Okay, if they have disturbed, then you will see these three plots, the 3 points in a dispersed manner. Okay, but if you want to do this with only the whole rocks, still okay, but there can be some errors, right? I mean, errors means uncertainties, right? Because whole rock might not be homogeneous equally. You are taking three whole rock samples. They represent three-dimensional locations in the space, because the sample is at different places. But you don't know actually this rock layer throughout these 3 points where you collected is homogeneous or not, right? So for the appearance it is homogeneous, it might be, but actually it might not be also, right? So then it can give you some troubles when you plot, right? That means you are getting very dispersed points. So in that case you will get a high standard deviation. That means statistically your line you are getting might not be the best fit line, right? So if you use different minerals and whole rocks, or even without whole rock, you can use just the minerals also. In that case, we call it mineral isochrone, right? If you just use only whole rock, then you call it whole rock isochrone. If it is a mixed isochrone, that is best, because you are certain that the minerals as well as the whole rock have remained in a closed system during this evolution. So you have to you have to see this error also, and also the standard deviation. Okay, so this error is given as 2 sigma. What is 2 sigma? Has anyone done oh, I think you have already done statistics, right? 2 sigma, two standard deviations, right? Two standard deviations, right? Sigma is the standard deviation. 2 times sigma is 2 sigma, right? That means more reasonable estimate, right? Statistically more reasonable estimate. And also you have to find out the MSWD. You remember mean standard weighted deviation, MSWD, that value. If it is close to 1, that is ideal. But the lower the number, like 1, 2, 3, 4, 5, 6, okay. But if you are getting like more than 20, 30, 40, something like that, then it might not be uh, precise enough, right? But in this case, you see, it's just 80 million year error is given, uncertainty is given, while your age is 4560. So this is a very good age. This is a very good age uh, compared to because this is four digits. Your error is 2 digits. Okay. If you are getting some error like 250 or something, then it's large. Even 100, above 100 is larger, right? Because your uncertainty is very high. Say if you are getting 250, that means that the age of the earth may be 4700 or 800, 4800, or even it can be 4300, 250 or something, right? Plus or minus, because this is plus or minus. You have to take it plus or minus, right? But anyway, the fair, the distribution, you will get more accurate age. Okay, right. So this is an example from some of one of the localities. There you see this isochron behavior. So it's a good isochron. This is a good isochron giving you the age. So to calculate the age, you can take the theta here, tan theta, and tan theta will give you, you can equalize tan theta into this value, right? E lambda t minus 1. From that, you can take t. You take it tan inverse and then you calculate it, t. Okay, so this is the theory for the neodymium system. And you have to remember this equation, age equation, right? This is a must. Okay, do you have any question? As I said before, the slope is very, very significant. Okay, this is a correct slope, because otherwise you get, even at a tiny difference, you get a different tan theta, and that will be giving you an enlarged error, because you are dealing with exponential or natural logarithmic value here, e lambda t, right? So if you have a tiny error, that will be enlarged when you make it to linear form. So therefore, that's why I mentioned the correct isochron should be used. Okay, so let's just see the evolution of this neodymium isotopic composition for the Earth. How do you see? This is time, and this is neodymium isotopic composition. The chondritic meteoritic value, that is before the formation of the Earth, right? The Earth was formed by chondrites. We call it chondrite uniform reservoir, CHUR, chondrite uniform reservoir, right? That is the uh, initial reservoir. The all planetary bodies were formed. That has an evolution like this. That means it is found, they had initially at the time of the Earth's differential, I mean Earth's for accretion, formation of the Earth, some value like here was there, right, for the chondrite uniform reservoir. So with time, this is 4.5 billion years, right? So with time, it evolved in a way producing more and more neodymium isotopic values like this, and it evolved with time. So in a manner like this. Okay, so actually this is the evolution line. So at about 3 billion years, close to 3 billion years, what happened? At about 3 billion years, very close to this age, Earth's differentiation was, uh, I mean, several differentiation events occurred. Remember, depleted mantle formation and continental crustal formation, like that. Right? So until that, normally the chondritic mantle was evolving. I think you can remember this evolution we talked about with rubidium strontium isotopic system also, right? About 2.7 about 2.7 billion years time. What happened? It is not mentioned here actually. What happened? The continental crust was also formed, right? Sorry, this is not continental crust. Sorry, we have to delete this part. Continental crust was also formed, right? Continental crust was enriched or depleted in neodymium. Enriched or depleted continental crust. Was it low or high? Just a while ago I mentioned it's opposite, right? That's why I made this mistake also, right? For the rubidium strontium system, it's okay, right? Should be opposite, right? So the continental crust should go like that because it has less neodymium. Why? Continental crust is a product of the melt, right? So what happens? Samarium likes the residue. It's more compatible than neodymium. So samarium decays to neodymium. So for the melt, you have less amount of samarium. So with time, it will produce less amount of neodymium. So definitely, compared to its origin, here, it should be deviating, show a deviating trend downwards. Okay, it is not mentioned here. You can draw it. This is continental crust, and for the enriched mantle, if the mantle is enriched means if more and more incompatible elements have gone into that mantle, because there is there is you remember we talked about the mantle and the mantle depletion, right? Lower mantle and upper mantle, right? Lower mantle is enriched. Lower mantle still contains, we told lower mantle still contains chondritic composition. Do you remember? Right? But upper mantle is depleted, right? Upper mantle is depleted. That means it is depleted in incompatible elements. So obviously it should be depleted in samarium. So therefore, samarium should, the depleted mantle should evolve in a giving a high neodymium isotopic values, right? This is nothing other than we talked the previous discussion, right here. See, this is depleted mantle, the residue. So it has high neodymium values, right? The continental crust, see here, it has low neodymium values, right? So same thing we are just repeating in different contexts. Okay, right. So continental crust will have low neodymium values, neodymium ratios with time, whereas the depleted mantle will have high neodymium values. The reason is they have high samarium neodymium ratio because more and more samarium has already gone to the residue part. Less samarium has gone into the melt part. That's why they are evolving like that, right? So if you want to show the chondritic uniform reservoir continuous evolution, if nothing happened to the earth, right, it will come even up to today like this, right? This is the chondritic evolution line, right? So with respect to the chondritic reservoir, you can talk about some of our rocks whether depleted in neodymium isotopic composition or enriched in neodymium isotopic composition, right? They have a low neodymium isotopic composition, or they have high neodymium isotopic composition. All right. So with respect to this chondritic uniform reservoir, we can just compare our rocks, our crustal rocks we can compare here, our mantle rocks we can compare here. All right. So remember, compared to the this chondritic reservoir, our crust should be what? Our crust should be enriched or depleted in neodymium isotopes. Crust should be low and mantle should be high with respect to the chondritic reservoir. So this chondritic reservoir concept is important because uh, you have to assume if it evolved until today without a disturbance from these partial melting events, we must be having some chondritic value of to present day chondritic value here. So this is 0 MA, this is 0 MA, that means today, present day. So you must have a chondritic isotopic, neodymium isotopic value today in our earth if nothing happened. But unfortunately or fortunately, we have continental crust and depleted mantle. They are showing very different isotopic values today. Okay, right. So mid-ocean ridge basalt, again, one thing. Mid-ocean ridge basalts are products of depleted mantle, right? You remember depleted mantle. Mid-ocean ridge basalts are products of depleted mantle. So this is depleted mantle. So how will they behave? That will produce a melt. So if here you see a melt produced, then what happened to the neodymium isotopic composition? It deviated downwards like this, right? When continental crust was formed. So if you produce mid-ocean ridge basalt by partial melting of upper mantle, upper region of the mantle here, this part, right? Mob is produced from this part, upper part of the mantle, right? So mob melt is going up. So what happens? Since it is melt, again there should be a deviation, so it should be deviation like this. So that's why here you see a basalt variation like this. Okay, so mid-ocean ridge basalt relative to the more DM depleted mantle will show little lower than the depleted mantle value. Okay, this is mob and this is depleted mantle value, because mob is still okay, mob is depleted, but mob is still melt. Therefore, there should be a little difference. So this is the difference, but it is much higher than the continental crustal values, right? Continental crustal values are here. This is the continental crustal values. Those are very low neodymium values, present day neodymium values. We are talking about the present day, right? So this is how the isotopic compositions evolve with time. Okay, right. Do you have any question? So I suggest you go back uh, to your home and or hostel and do the revision again, right? Starting from the rubidium strontium system and compare it with the samarium neodymium system, and try to understand its contrast and similarities, right? Actually, no similar. I mean, the contrast is the most important thing, because the behavior of parent and daughter is different. That's why. Okay, so I think we will stop here if you don't have any more questions. But remember, this part is very, very important, right? Because we will be discussing something totally different from rubidium strontium system next week. Uh, with because something identical to the samarium neodymium system, right? So for that, this the chondritic uniform reservoir is important. So therefore, just have the concept behind this churn. Okay, right. So we will stop here for today then. So sign the attendance and submit to the office.